Welcome to Easy Math, guys. Today we are going to be looking at exponents and radicals. Exponents and radicals. So an exponent is simply an expression of the form a to the n, where a is called the base and the n is called the exponent. N is called the exponent. Okay, this is an exponential expression, while a radical is any expression of the form x, like that, where n is called the index of the radical, and our symbol there is called the radical sign, and x is called the radicand, x is called the radicand. So any expression that takes this form is an exponent or an exponential expression, while any expression that takes this form is a radical expression. So exponents and radicals are governed by some laws, right? These laws are usually used to basically simplify exponential and radical expressions. These laws are used to simplify expressions. So I'll start with a quick recap of the laws of exponents. So the first law they see is if you are multiplying two expressions with the same base, then you can simplify that by adding up their powers, okay? For example, if you have 2 squared times 2 cubed, then you can simplify this by adding up the powers, 2 to the 2 plus 3, which becomes 2 to the 5, right? That's what that first law says. So this applies not just to single constants, but to entire expressions. For instance, if I have x plus 1 squared times x plus 1 cubed, right? I can still simplify this by saying it's then equal to x plus 1 to the power 2 plus 3, which is x plus 1 to the 5, all right? So my x there represents entire expressions as well as constants, not just constants alone. So the same thing applies to all the other bases in the rest of the the expressions in the laws. So the second law says that if you are dividing two expressions with the same base, you can simplify that by subtracting their powers instead, all right? And the third law, which is just the second law is actually a generalization of the third law. So the third law says that the reciprocal of x to the n is actually x to the minus n. So you can move your x to the n to and from the denominator by negating the exponent, right? So if you want your n to move up to the numerator, you negate the exponent. If you want it to come back down, you still negate the exponent. Okay, this fourth law says that any expression raised to the power 0 is 1. Any expression at all, whether 7 to the power 0 is 1, 10 to the power 0 is 1, 3x plus 5 all raised to the power 0 is 1, and so on. That's what this law says. And this law says that if you have two powers like this, you can just multiply them. This is quite straightforward. Then this law is the distributive law, which says you can distribute the exponent to every expression in the bracket there, like that. You can actually distribute the exponent to every expression in the bracket and in the bracket in the product, right? This is for product distribution, and this is quotient distribution. So this law also says that in any quotient, you can distribute the power to each of the expressions in your quotient, like that. So we are going to see how to apply these very soon in simplifying expressions. Then we have the law of radicals, the laws of radicals. The first one says the nth root of x can also be written as x to the 1 over n. So this law is actually the law that is used to write radicals in their exponential forms and exponents in their radical forms. So that's this law. It's one of the most important laws of radicals and exponents, as we will see much later. Then the second law of radicals says that you can actually combine two different radicals into one radical sign like that if their indices are the same. All right, if their indices are the same. So the nth root of x, nth root of y, n is the same as n, same index, you can write it as one radical sign, one radical expression. Okay, then this law says that nth root of nth root of x is actually, so you can also combine these two and multiply their indices. Okay, these are laws that you can use to actually simplify expressions. Then this law says that x to the, so this law is a generalization of this one, all right, of that first one. X to the m over n can be written as the nth root of x to the m, which is also the nth root of x all raised to the power m. So it's a change from exponents to radicals and vice versa. And this law says that if the index and the power are the same, then they cancel each other and we just end up with the radicand alone. Okay, that's a quick recap of the laws of exponents. You can find these laws in your textbook and have a detailed look at them. So I'd like us to move straight into looking at a couple of examples, how we can apply these laws in solving or simplifying mathematical algebraic expressions. How can we apply some of these laws in simplifying math expressions? Okay, so the textbook I'll be using to do my examples is the Introductory Mathematical Analysis for Business Economics and Life and Social Sciences, the 13th edition. So I'll be using the 13th edition, but the examples are much less the same as those in the 14th edition, all right? So since we will be doing most of the 14th edition examples in class, I've decided to make this video using the 13th edition examples. It's just to give you a wider scope. Okay, so I'll just pick examples randomly. I'm looking at problems 0.3 of Introductory Mathematical Analysis, problem 0.3 right now. So if I look at number 2 of problem 0.3, number 2, so it's problems 0.3. And if I look at number 2 there, so number 2 says simplify the following expressions. So we are looking at simplify the following expressions. So the first one, this number 2 is x to the 6 times x to the 9, and we want to simplify. So our first law of exponents applies here. When you are multiplying two expressions with the same base, you can simplify by adding up their powers. All right, so this just becomes x to the 6 plus 9, which is actually x to the 15. Quite straightforward. So that was number 2 of problem 0.3. I also like to look at number 6. So I'll start with the basic ones and then graduate into the a bit more complicated ones. So this one says given x to the power 12 times 4, right? We need to simplify this. So this just turns out to be, so we use log, the fifth law there, fifth law of exponents, which says this is just as good as multiplying these powers, all right, to simplify your expression. Okay, let's quickly look at number 10. Number 10, we are still in problem 0.3. So number 10 says simplify w squared s cubed or w squared s cubed divided by y squared or raised to the power 2. Okay, simplify this. So in order to simplify this, right, we need to start by opening up the brackets. We can start by opening up the brackets as well as evaluating the brackets first, all right? But I would like to start by opening up my brackets using the distribution law. So the distribution law says I can distribute this power to, and that's that's the sixth law of our laws of exponents. So by sixth law, I mean the order I'm using is according to this order here. All right, it might be different in your textbook or in different textbooks. Law 1 could be this law, law 2, this law, it doesn't matter. So when I say sixth law, I'm talking about this order. Take note of that. All right, so this is the distributive law, and that's the law I'll be starting with to simplify this expression by distributing this 2 to each expression in our bracket there, in the quotient there. So it then becomes w to the 2 times 2, s to the 3 times 2 divided by y to the 2 times 2, which is then equal to w to the 4, s to the 6 over y to the 4, right? And since my bases are all different, I can't simplify this any further. And so that this is then my final answer to that question, number 10. Okay, then we also look at number 12. I think number 12 is also the same as 10. I'll rather look at number 14. Number 14, so it's x squared. We are still simplifying all of this cubed times x cubed, all of this squared, divided by x cubed raised to the power 4. Okay, so again, we are going to start with our law 5, which says we can just multiply these powers, all right? We start with law 5, simplifying each expression in the quotient first. So the first one becomes x to the 2 times 3, which is x to the 6. Next one, x to the 6 as well, divided by x to the 12, all right? Then we apply law 2 to the numerator, which says if you are multiplying expressions with the same base, you can simplify them by adding up their powers. So if we apply law 2 to the numerator, it becomes x to the 12, all right, 6 plus 6, divided by x to the 12, all right? And finally, we apply law 2. Okay, this was law 1. Sorry, we are applying law 1 to the numerator, not law 2. And then we apply law 2, which says if you are dividing expressions with the same base, you can simplify them by subtracting their powers. So if we apply law 2 then to this expression, we get our final answer, which is x to the 12 minus 12, which is x to the 0. And by our third law, right, the fourth law in the order in which we are using in this video, any expression raised to the power is 1, to the power 0 is 1. So this is then just equal to 1. So that's what this expression basically simplifies to. Okay, so that's how to use these laws to simplify expressions. Let's simplify even further. So if you look at question 18, let's take a look at question 18 there. So I want like us to look at number 18. 18. Number 18. So number 18 says, without the use of calculator, evaluate these expressions. So you need to evaluate these expressions using your laws of exponents without using your calculator. All right. But there are certain ways in which you can use your calculator to find out things, but then still show your steps using your laws of exponents. So 18 says we should simplify or evaluate the cube root of 0,027. 027. Okay, we should evaluate this cube root of this 0.027 here using our laws of exponents. So this is a given radical, all right, and I should be looking at which of the radical laws of radicals can help me in evaluating this expression here. So the first thing I want to do is to quickly look at my law, this law over here. Okay, law 5. So law 5 says that I can actually simplify this radical so easily if the index and the power are the same. Okay, so what I can do here is to strive to make the index and the power the same without changing this expression. If I can do that, then I can easily evaluate what this cube root is. Okay, so how can I write this as the cube of something? That's the question now, because I want my index and my power to be the same. So my question is, I ask myself, how can I write 0.027 as some number cubed? All right. So I look at this 0.027. If you remember the old primary school method where to convert this decimal to a fraction, we move the decimal we move the decimal to all the number of places to the right. So if we move this decimal, it becomes, we move it to 1 place, 2 place, 3 places to the right. All right. And what we have in there becomes what we have in the radicand becomes 27 over 1,000. All right, because the 3 places represent the 3 zeros, 10 to the power 3. 1, 2, 3. Okay, so it gives me a 27 over 1,000. So you can also quickly just use your calculator to change 0.2027 to fraction, and you get this value, right? So that's the only way you can use your calculator in this type of questions without the examiner knowing that you used your calculator. Okay, it's just in being able to change this decimal to a corresponding fraction. So now once this is done, you can then go ahead and then ask yourself again, how can I write this as the cube of some number? So I know that 27 is 3 cubed. I can also use my calculator to get that. And 1,000 is 10 cubed. So 27 over 1,000 is basically 3 over 10 cubed. All right, 3 over 10, all of this cubed gives me 27 over 1,000. Okay, and then by my law 5 of radicals, we are told that if the index and the power are then the same, they cancel each other and we are left with just the radicand. Okay, and therefore our answer is 3 over 10. So this the cube root of 0.027 is basically 3 over 10. Okay, let's take a few more examples. Before we round off this video. One more example, then we round off this video and move to the next one for the sake of the length of the video. So this example is number 20. Number 20 of the same 0 point problems, 0.3. So number 20 says, number 20 of 0.3, it says evaluate, okay, the expression cube root of -8 over 27. Okay, evaluate this expression. So we are going to be applying the same method we applied in the previous question to evaluate this expression. All right, by trying to write our radicand as the cube of some expression or some number. If we can be able to do that, then the radical sign and the index are going to cancel each other, and we'll be left with just the radicand as our solution. So I ask myself, 8 can be written as the cube of what? -8 in particular can be written as the cube of -2, while 27 can be written as the cube of 3, right? So therefore, this expression is just the same as cube root of -2 over 3, all of this cubed. Okay, you can always use your calculator to find out what it is as the cube of something, all right? You can always use your calculator to find out that by just looking for the cube root of 8. So the cube root of 8 will be 2, and the cube root of 27 will be 3, so which tells you that 2 cubed is 8, and 3 cubed is 27. So once we have it this way by our law, radical sign and this power here go away, all right? They disappear. And why do they disappear? They disappear by this law here. Let me just write this by the side. This law which says that x to the n over m is x to the n over m is the nth root of x, m root of x to the n, basically, all right? So much so that if my n is the same as m, so it becomes x to the m over m is mth root of x to the m, all right? So the m and the m cancel each other, and this just boils down to x to the 1, which is just x. All right, this is how the cancellation process takes place, basically. Okay, so I just needed to show you that, so much so that, for instance, cube root of 2 cubed cube root, for instance, using this law, as an exponent, it will be written as 2 to the 3 over 3. Okay, 3 divided by 3 is 1, so it becomes 2 to the 1, which is just 2. So this is how these guys do cancel, all right? It's using that change from exponents to radical that we already saw in one of our laws. Okay, so when I say that they cancel each other, it's not just by magic. That's actually how the cancellation works. Okay, so at this stage then, using what I've just illustrated, we can then say that our answer is -2 over 3. Okay, and that is the evaluation of this cube root here. Okay, let's take this other example, question 28. Number 28. Number 28. So number 28 says that we should evaluate. 28 says we should evaluate -27 over 64 to the power 4 over 3. -27 over 64 to the power 4 over 3. Again, the same method applies. So notice that this question and this one are exactly the same type of question, all right? It's just that this one was written in radical form, while this one was given to us in exponential form. okay? Because we can still write this exponential form in its corresponding radical form. So in this case, what I want to do is to then, I can decide to distribute this to each of these, all right? Or I can, okay, let's do it that way by distributing first. So it becomes a negative 27, negative 27 to the 4 over 3 divided by 64 to the 4 over 3 by one of our distributive laws of exponents. You can do this. All right. Otherwise, you can write this as the cube of something so that your cube is going to cancel out with the 3 like we just illustrated above. Okay, that's also another way. Okay, so this said, we can then write 27. Okay, so notice that this in its radical form will be negative 27 cube root all to the power 4 divided by 64 cube root all to the power 4 as well. All right. Okay, so next thing I'm asking myself, how can I write 27 as the cube of something, cube of some number? So if I can manage to write 27 as a cube of some number, then the radical and the power exponent will cancel each other again by our law 5 of radicals. So I know that 27 is 3 cubed. So negative 27 will therefore be negative 3 cubed. So this whole expression becomes cube root of minus 3 cubed all to the power 4 divided by cube root of 64 is 4 cubed. So as I said, you can get this by just looking for the cube root of 64 in your calculator. Then it gives you 4. So it tells you 4 cubed is 64. All right. 4 cubed there, all to the power 4. Okay. So by our law, this entire radical becomes negative 3, while this entire one becomes 4. Okay, so it becomes negative 3 over 4 all to the power 4. Okay, and then you can then evaluate that, or you leave your answer like that. Leave your answer like that, or you evaluate this answer using your calculator, basically, to get the final answer. Okay, negative 3 to the 4 over 4 to the 4. Okay, so that's that. And then we then move over to the last one before the end of this video. So this last one says simplify the following expression. Simplify the following expression. And our given expression, this is number 35. Okay, of the same 0.3. Our given expression there is 2 times, I think this is too close. Need some space here. Okay. Our given expression is, so this answer here was minus equal to minus 3 over 4 to the power 4, which you can evaluate with your calculator. Okay, so this number 35 is 2 square root of 8 minus 5 square root of 27 plus cube root of 128. Okay, and we want to evaluate this using our laws of exponents. We want to evaluate this using our laws of exponents. So again, I'm trying to simplify here. All right, so 8 is not a perfect square, so it will be difficult for me to find the square root of 8, okay, without using a calculator. So what I can do is to write it as the product of a perfect square and a non-perfect square. All right. So it becomes to me, so this expression then turns out to be 2 square root of 4 times 2. All right. Because 4 is a perfect square and I know what its square root is. Okay. Minus 5 times square root of 27 also is not a perfect square. By perfect square, I mean a number whose square root is a whole number. All right, a number whose square root is a whole number, not decimals. A number whose square root is a whole number. For instance, 4 is a perfect square because its square root is 2. 9 is a perfect square because its square root is 3. All right, 16 is a perfect square because its square root is 4. Okay, 8 is not a perfect square because its square root is 2 point something. 10 is not a perfect square because its square root is 3 point something, and so on. So 27 is also not a perfect square because its square root will be 5 point something. So but then I can write it as the product of a perfect square and a non-perfect square. And the perfect square I can think of there is 9 times 3. It's my 27 plus cube root of 128. And I think 128 also is not a perfect cubed, right? 128 is also not a perfect cube. So we can try to write 128 as the product of 128 is also not a perfect cube, but we can write it as the product of 64 and 2, where 64 is then a perfect cube, right? Because the cube root of 64 is 4. So then I move over and try to simplify these. So this becomes 2 times root 4 root 2 minus 5 root 9 root 3. So one of our laws of exponents permits us to write square root of 4 times 2 as square root of 4 times square root of 2. All right, revert back to your laws of exponents and you'll see that we can actually distribute the radical sign to products and quotients in our radicand. And square root of 64 cube root actually of 64 cube root of 2. Okay, so that said, I can then simplify. Square root of 2 is 2 times this 2, it becomes a 4 root 2 minus square root of 9 is 3 times this 5, it becomes a 15 root 3 plus cube root of 64 is a 4 cube root of 2. Okay, and so we can't simplify this any further. So this is then our final answer. Okay, thank you so much. I'll see you in the next video.